everyone, welcome back to my channel. Today we will be focusing on the second topic of our syllabus, which is atoms, molecules, and stoichiometry. Like the previous video, I will put timestamps in this video as well. Um, Also, I would just like to mention that this topic is a relatively shorter one, but it requires the most amount of work. So you need to practice more and more to be able to kind of solve the questions. It's not really a topic that occurs on its own. It usually accompanies other questions and topics. It's like very integrated. And I do have a worksheet on this, which I will upload after this video. So let's get started. Our first part, relative masses. This is just another definition that you need to know. So we have the atomic mass unit, relative atomic mass, isotopic mass, and molecular mass. You just have to know all of these definitions. So when we talk about stoichiometry, it's calculations and a form of, let's say, standardization in chemistry. So what we have, our carbon 12 atom, this is our basis on which a lot of stoichiometric concepts are formed. Hence, we assume that a carbon 12 atom, like I'm just saying this to help you get the concept. Assuming that carbon 12 atom has, let's say, a mass of 12. We don't know 12 what, but let's just assume 12. So when we talk about relative atomic mass, it basically means the average mass of one atom compared to 1/12th the mass of the carbon 12 isotope. So for example, if carbon 12 has a mass of 12, then 1/12th of that mass is 1. That's the average mass of one atom, which is 1. That's basically what relative atomic mass is trying to say. You compare all other atoms to the standard, which is carbon 12. And that's where you get all the other definitions from. Except for this molecular mass, which is the mass of all the atoms in one molecule of a simple molecular structure. There's a way of calculating this. You just simply have to add all the masses of the atoms. And usually the periodic table helps in calculating this, which we will do. Okay, so the next thing, these are all just definitions which you do have to memorize because it's usually an easy 1 or 2 mark question. So you have the Avogadro's constant. Now this is a number 6.02 times 10 to the power 23. And this is the number of particles, atoms, molecules, let's say anything basically. It's not really specified to the number of atoms. Avogadro's constant is unique because it's the number of whatever substance you have in a mole of atoms or particles, like a mole of an element. So for example, the number of atoms in 12 grams of carbon 12. So 12 grams of carbon 12 is basically 1 mole of carbon 12 because it's the standard. So if we talk about the definition of a mole, the amount of any substance containing as many particles as there are carbon atoms in 12 grams of carbon 12. So the mole is like 1 mole of carbon 12. So like 1 mole of carbon 12, it has 6.02 times 10 to the power 23 atoms present. So that means 12 grams of carbon 12 has this many atoms present. That's essentially what this whole concept means. It may sound confusing, but it gets easier. So, for example, I just want to show you the periodic table so that you get it. So, as you can see, we have a carbon 12 here. So, 12, right? This has a relative atomic mass of 12. And as we saw in the definition, relative atomic mass is 1/12 of the mass of carbon 12. So the relative atomic mass of carbon 12 itself would be 1/12 of this 12. And that's just one, right? So that's what we have. And then if we have magnesium, in IGs, you don't have this this decimal place, this first decimal place. You just have 24. So this would rather be 2. It's like, let's say, atomic mass relative to carbon 12. So that's just to say magnesium is twice as heavy as carbon 12. This magnesium atom would be twice as heavy as this carbon atom here. That's what kind of relative atomic mass means. And one mole of 1 mole of carbon 12 is not the same as 1 mole of magnesium. Even though they have the same number of atoms, it's not the same because of the relative atomic masses. And that's also a concept that helps a lot in stoichiometry. So that's for that. I will explain this further when we're doing the worksheet because it makes it so much simpler when you actually solve questions. I do have some questions at the end of this note which we will solve. So the next thing to look at are formulas, chemical formulas. So first things first, ionic compounds, which we do know from IGCSE how to drive ionic compounds. It's the same principle. There's nothing new about this. Uh, the charges I've written are just the valence. The charges I've written are the ionic charges. So when these individual groups have their atoms becoming ions, these are the charges those atoms possess. It's very simple. So you have lithium chloride, lithium is +1 and chlorine is -1. So you only need one lithium atom and one chlorine atom to bond and form lithium chloride. An ionic bond is essentially between a metal and a non-metal. However, in A levels, what we have are ionic compounds. You see in IGs, it's like strictly metal, non-metal, but you do have certain compounds that are metal, non-metal, and they are not ionic. For example, we can have aluminium chloride, and this is not ionic. This is covalent. It We call this as to having more covalent character than ionic character. It's like a scale where this is, let's say, ionic and this is covalent, and this is the middle, which is probably neither, but there's not really a neither compound. So the covalent one, that's where the aluminium chloride would be found. And then you have like your sodium chloride, and that would mostly be here. So it's a scale really, and there's not really much to determine how but all the exceptions will be given to you. It is assumed, however, that any non-metal and metal do form ionic bonds, hence they are an ionic compound. So you have your lithium chloride, your magnesium fluoride, and so on. And then we have our transition metals, which obviously do have variable oxidation states, which means that unlike a very determined charge on each of these groups, our transition metals here, this whole block, they would rather have different charges when they form ions. So for example, iron could be 2 plus, 3 plus, and so on. So iron can either form FeO2 or FeO3. And usually when you list these compounds in words, when you write them in words, you have to mention whether it's iron 3 or iron 2. So you usually say it like this: iron 2 oxide or iron 3 oxide. And that's just how you go about it for the transition elements. Next, yeah, that's just what I was mentioning here. You need to mention the value of the charge in Roman numerals in brackets. Then we have other ions. These are radicals. These are usually like a group. They come together. You can't separate them. You have your hydroxide. So hydroxide as in you have a base sodium hydroxide. Sodium has a charge of +1, and this whole hydroxide radical has a charge of -1. I call it a radical since it's a species with one or more unpaired electron, as that was the definition in the previous video I'm explained. Then you have nitrate, which is 3, which has this O3, but it also has a charge of minus. This is sulfate SO4 2 minus. And then as you can see, all of these are either minuses or pluses. And you have to know what all of these individual radicals and their charges are, because they are very common compounds, and usually when you go on with the syllabus, they come to your fingertips naturally. So I wouldn't really say memorize, but as you go on, you will know them. You do sometimes need to know some of the odd ones, like there's a difference between a phosphate and a phosphite, or a sulfate and sulfite, and so on. But that comes very later when we're discussing period 3 or when we're discussing group 2, let's say. Some of these things will come in handy then. So that's for ionic compounds. Then we have ionic equations. Ionic equations is something that was introduced in IGCSE. However, in A levels, it's kind of more extensive, but we go deeper into it during redox reactions. And that's, I think, chapter 8, if I'm not wrong. So basically, ionic equations, as you can tell from the name, you have ions, but you only have them on one side. So sodium chloride, when you're forming it, you can have the sodium ion, the chloride ion. You need to write them with their charges, and then you have the sodium chloride compound, which also needs to have their state symbols. There's aqueous, gas, liquid, and solid. So the ions need to the equation has to be balanced. So for example, this plus and minus, when you add them on this side of the equation, the left hand side, the total charge is 0, and the right hand side also, it's 0. Then you can have barium, which has 2 plus, and then sulfate, which is 2 minus. So 2 plus and 2 minus is also 0, and then barium sulfate is 0. Barium sulfate forms a precipitate, which is basically like a solid formed within. So like, let's say, I'm just going to use this to explain. Let's say we had the barium ions here in water, like aqueous, and then you have your sulfate being added to it, and then this will slowly form some kind of solid that will like deposit in the test tube. or whatever container you're doing your reaction in, and that solid is the precipitate. Barium sulfate is white, and you'll see this when you do reactions in the lab for paper 3. Usually you see a white PPT. It's almost always barium sulfate, especially when the starting material is a compound that has the sulfate ion. So that's usually kind of a hack I used to use. If a compound has the sulfate ion and you're using it in any experiment, then a white PPT forms with an unknown other compound, then you can be sure that there was a sulfate ion. Uh, it may sound very complicated, but it's not. So that's for ionic equations. Sometimes, however, you don't have a neutral charge on the right side, and you do have an imbalance of charges, but that's for redox reactions, and it's for another chapter. This was just to give you a basic idea. So we have empirical formula. Similar to IGs, the simplest whole number ratio of atoms of each element in a compound. So example, we have hydrogen peroxide, which is H2O2. Now its empirical formula, it says the simplest whole ratio. So the ratio of hydrogen to oxygen is 2:2, but we can simplify that to 1:1. So its empirical formula would be HO. However, that's not really accurate, but empirical formula does help you to get the eventual kind of ratio and percentages of how many atoms are there relative to each other. So it is helpful at times, but not when you need to do calculations and stuff. For that, you can often transform the empirical formula to a molecular formula, and that is the actual number of atoms of each element in a compound. So our hydrogen peroxide would be H2O2, and that is the molecular formula. Then we have some other terms like anhydrous, which means without water, hydrated, which means has water in its chemical structure. Then we have water of crystallization. This is kind of different from hydrated. Hydrated could usually mean the compound is just dissolved in water, but water of crystallization is when water is like part of a crystal structure. So you have this copper sulfate with associated with 4 water molecules. These 4 water molecules are associated with the crystal structure of this compound. It's not really as if it's aqueous to say. This compound can be found in a solid, and then you heat it up, and all of the water kind of like um, evaporates, and then this compound is usually blue, and then it changes to white, I believe. There's also cobalt chloride, which is similar, and then that changes from, I believe, pink to blue or blue to pink. These two compounds, copper sulfate um, with the water of crystallization, and then the cobalt chloride I usually use to test for water in a compound. Okay, so we've actually come to the end of all the content we need per se, but obviously it's not really enough. We do need to do some calculations. I will have some in this video, and then I will have some in another video, which I will do separate just for this topic, and it'll be heavy on calculations. So these are just examples. So the first question we have says, this diagram shows the skeletal formula of phenazine, phenazine, whatever you want to call it. And then we're asked what is the empirical formula of phenazine. So we have phenazine here. I wrote some of the atoms, I drew them, the full structure, so that we could easily determine this. Because this compound is an organic one, and you would need to know what this looks like in organic chemistry, but we haven't gotten there yet, so I just simplified it. So we can count the number of carbon atoms, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have C12. Then we need to count the number of, let's say, nitrogens first. There's only two, so that's N2. Then we need to count the number of hydrogens. So we have 1, 2, 3, 4. Same on the other side, so that's 8. So we have H8. Now the empirical formula, we need to simplify this ratio. So I would just cancel out the 2, and this becomes 6, and this becomes 4. So we have C6N H4. And when we're looking for it, I believe A is our answer because that matches. And that's just how to do this. This is a very simple question. And that's how you determine the empirical formula from looking at the molecule itself in, like, I wouldn't say plain sight, but yeah. So we're done with this question. These are some formulas that you will need for calculations eventually. Just some basics. You have mole is equal to mass over molar mass. So the amount of moles of an element or a compound will be equal to the mass of that element or compound over its molar mass. That's this formula, and it's one of the most useful formulas ever. You have percentage yield, which is actual, let's say, mass. So once you do an experiment, the actual mass that you weigh of that product that you get, that's what this would be, the actual mass slash moles over the theoretical, which is the calculated one that you expected. Mostly the theoretical one is way more than the actual one because of certain lab conditions. So this is to calculate the percentage yield. Sometimes you get percentage purity, which is pure, the impure substance, and then you're supposed to do some calculations to figure out how pure it is. And there should be questions on that, which we will tackle as well. Then you have this other formula for moles, which is concentration times volume. And you can even see in the units, concentration is basically moles divided by dm cubed, which is the unit for volume. So when you multiply both of these, the dm cubes cancel and you get moles. So that's essentially this equation. Then you have this fourth one. This, now you see, this is concentration and this is volume. And when you multiply them, you get moles, right? So this is essentially saying that, let's say we have a substance like sodium hydroxide, and you're kind of diluting it. So you use, like, let's say 50 dm cube of water. That's like the volume 1. And then this sodium hydroxide has a certain concentration, which is this concentration. So when you multiply that concentration, let's say it's 1 times the 50 dm cube, what you get is your moles. So if this is 1 mole per dm cube, so in 50 dm cube, you would get 50 moles of sodium hydroxide. And essentially, what this is used to calculate is that if initially we have, let's say, this 50 moles of sodium hydroxide, and we want to reduce its concentration to, let's say, from 1 mole to 0.5 moles per dm cube, then how much, let's say, volume of water would we need to add, or how much volume would we have, then that's where this comes in handy. It's kind of like the P1 V1 equals P2 V2 kind of thing in physics. That's what kind of I can relate this to. It's essentially the initial conditions and the conditions afterwards. And it's really useful. Then we have 1 mole of any gas at RTP is 24 dm cube. So let's say you have 1 mole of oxygen at room temperature and pressure. This condition is given to you at the end of every single A-level examination you will take. It's always given. There's a certain booklet or a page, and I will show that to you. That's you will be given the conditions. So let's say 1 mole of oxygen gas at room temperature is 24 dm cubed. That's the volume 1 mole of oxygen gas will occupy at room temperature. Standard temperature and pressure is different, so that would be 22.4 dm cubed instead of 24. We don't often deal with standard temperature and pressure, but it's advised that you always read the question properly because you never know. However, mostly it is room temperature and pressure. Room temperature and pressure is just 25 degrees Celsius and 1 atmosphere. But I believe standard temperature and pressure is kind of different. Okay, so we have 1 mole of atoms, ions, molecules is 6.2 times 10 to the power 23 number of particles. So 1 mole of, let's say, carbon atoms contains, wait, 1 mole of carbon contains, let's say, this many number, 6.02 times 10 to the power 23 number of particles. Like, that's basically what this is. It's the relationship between moles and the Avogadro's constant. They are always linked together. And with that, we come to the end of our chapter 2. I will show you guys the syllabus like I did last time. So here we have the syllabus. We have ticked everything we need. You can check this because I've already explained all of these. So we can write formulas, we know how to determine the ionic charge, the names, the equations, state symbols, and everything. So yeah, what we need to do are the calculations, which I will do in a part 2 or a worksheet kind of video. So this is everything that I will cover in the next video. So for now, this is all of the theoretical content that we need. And yeah, I will see you guys in the next video. As mentioned earlier, I will have timestamps, and I hope that you guys liked it. I hope this is useful. If you have any questions, please leave it in the comment section, and I will see you guys in the next video. Like and subscribe. Bye.